Away. Okay. I want to welcome you to the William W. Hay Railroad Engineering Seminar at the University of Illinois. And before I introduce our speaker, I need to take a few minutes and cover a few housekeeping items. First, if you have a cell phone, please turn it off or put it on vibrate. Second, if we have a fire alarm, we can exit from either side of the room. There's stairways if you go out to the left in that direction, and immediately to the right if you go out this door. Take it down to the ground floor, and we will meet on the other side of Main Street by the Hydro Systems Lab. Please use a buddy system. Look at who's next to you, and if this event occurs and we have to go out there, make sure you find them once you get out there. Please be sure to sign the attendance sheet that's going around if you already haven't done so. We use this not only for the lunch we provide, but also email announcements and just to get an idea of how many people are at the seminar. And so, Tim, I gave you bad information before. When it comes around, please sign it. I would like to welcome those of you who are joining us by the phone. We have, right now, it looks like at least 30 online participants from a number of organizations, Parsons, Michigan Tech, Union Pacific, CSX, TV Rail, URS Corp, ESI, RK&K, Metra, CP Rail, the Army Corps Civil Engineering Lab here in Champaign, and TTCI, as well as a few others that I haven't mentioned. One last thing, I would like to ask our speaker, Dr. Kish, that at the end when we do question and answers that he would repeat the question from the audience for the benefit of the telephone or online audience so they can hear the question as well as the answer. With that, I'm going to call on Matt Grieve to make any announcements for our ARIMA student chapter. So Matt, if you could come up for a minute. Sorry to get you in a...
All right, everybody. The ARIMA student chapter is going to be holding a happy hour in honor of our speaker today. It's going to be at 5:30 at the Blind Pig on Neal Street. Blind Pig Brewery on Neal Street. We will be outside in the beer garden. So first time this year, so get excited.
One last item on the housekeeping that I was asked by Angie to bring up. I think the official policy is we're not supposed to eat in this room, bring food or drink. I was a violator of that policy this afternoon, and I noticed there were several others. So when we're done today and you leave, make sure you clean up behind yourself and don't leave any mess in the room.
try to get those fixed.
Okay, so again, these are parts of the track lateral mechanism. And again, the three events, number one is the initial defect generation, number two, the growth of these defects on the load, and third is when the defects become unstable in the presence of high compressive forces, we get suddenly track buckling. Again, many parameters involved, and we'll touch upon these in just a bit. But it's important to distinguish between number two and number three, namely between track shift and track buckling. Basically, track shift asks the question of what is the maximum allowable net lateral load into the track structure to keep the geometry limits within safe values. Basically, as you know, as we increase the lateral load into the track structure, you get deflections on the multiple load passes, as shown over here in this figure in the bottom. Basically, on the left axis is the cumulative deflection on the lateral load. The bottom axis is the number of axial passes. And you know, if you apply higher lateral load, we get larger deflections. If we get low lateral loads, we may get none. The key thing is to find the one that's safe from the operational perspective. So basically, this is a high axial load problem, a load deflection problem, as opposed to the track buckling problem, which basically asks the question of what is the maximum allowable thermal force into the rail tie structure to prevent the sudden instability that you see over here. And here the issue is find those parameters that govern this response, and we talk about the mechanism on this just a bit later on. Now, good thing is that we have models for these available. There's a model called TRADA for track shift. That's short for track residual deflection analysis. And for buckling, we have program called CWR Safe. These were developed and tested by the USDT Voltage Center in the mid-90s, and they're the ones that we use currently for analysis purposes. Okay, so what? What do we care about this problem? Why important? Why is there a big worry on the industry side and FRA side? Well, the answer is that according to the FRA's accident statistics that track these accidents and derailments, track buckling ranks number one in all the track derailments. They have 65 close codes, and track shift ranks number 12. Not only that, but these buckle tracks are very expensive in terms of derailments, and in fact that ranks also number one as far as the dollar damage per derailments. These are very serious problems to the industry, and basically they're concerned about improving the reduction of these derailments to these modes. If you haven't seen buckle track before, it's nasty consequences. And the problem is that these incipient buckles are very difficult to detect. They happen suddenly under the moving train, so it's a dynamic event. And of course, they can cause derailments. As I mentioned before, in the US, we have many derailments a year. One example back 2 years ago, we had 27 mainline derailments at a cost of almost $1 million per derailment. This does not include injuries, fatalities, emergency response, evacuations, and so on. So that figure is actually much higher. So it's a serious event, serious problem. Railroads also experience many incidents of track buckles or sun kinks, which do not result in derailments. That's of course a high cost item for the repair point of view. And this last one, we always think about buckling to be a hot weather compressive force problem. It turns out that winter conditions, when the rails are in tension, causing occasional pour parts and rail breaks, that also contributes to track buckling, as we'll see in just a bit. So, how to prevent? Well, the 3 golden rules for preventing track buckles is 1, keep the thermal forces within safe levels, which really means manage this parameter called neutral temperature, and we'll talk more about that later on. Ensure good track conditions, and particularly when it comes to the ballast lateral resistance and the track's alignment defect condition. And lastly, control train dynamics and loads to the extent that's possible. And here we have to think about speed restrictions at certain times. The question is when and where. Seems easy, right? Not so, because the problem is to determine what these safe levels are and how to manage the neutral temperature in line with those safe levels. Also, what are good track conditions? Well, no, pretty much they're when they're good or in between. But many times when we maintain a railroad, especially ballast, that gets very weak, and that gives us a lot of concerns in terms of offering the resistance required to prevent buckle track. With the last item, the issue is when to impose speed restrictions, what temperatures, and where. All over the railroad, or just local trouble spots. So we'll touch upon some of these just a bit, but let's get back to the basics. What is track buckling defined as? It's nothing more than the formation of large lateral displacements due to three events happening, or due to the combination of three events. Number one, high compressive forces, weakened track conditions, and vehicle loads. Under the first one, the compressive forces are basically temperature-induced loads due to the difference between the real temperature and the neutral temperature, and then we'll talk more about that later on. Weakened track conditions are basically due to reduced track lateral resistance from the ballast perspective, and of course alignment defects. And the vehicle loads themselves, they don't produce buckles directly. What they do is they impact these other two parameters, namely dynamic uplift causes impacts on track's lateral resistance. High axle loads give us more alignment defects, and braking and traction loads add to the compressive forces and also impact the rail neutral temperature. So, what's the mechanism? It's good to begin a little bit with Mechanics 101. We all know there's a simple beam under uniaxial compression, load P. That beam stays straight until we reach a certain value of peak critical, at which time suddenly it buckles out into the configuration you see over there. And if you're going to plot the load deflection, or P versus W deflection, you get a simple curve in the curve you see over here, where up to some load peak critical, there's low deflection. But beyond that, once it buckles out, you get deflection, obviously. If you increase the load beyond that, you get more and more deflections. Very simple. We all know this problem from basic mechanics. It's good to think about this in the context of the railroad track, because if you think the track to be the beam itself, simplifies substantially. The thermal load now becomes the load P, but now it becomes a bit more complex, because we have added parameters such as ballast resistance, we have misalignments, we have tangent versus curved tracks, we have vehicle loads acting into the track system also. So it's much more complex, obviously. But the good news is that the temperature load deflection behavior is very similar for our track as well, just like we've seen over there. The bad news is that because of the problem complexity, the many parameters involved, being a dynamic problem, our current theoretical mechanics does not allow us to determine the exact value where this buckle occurs. The good news is that we have some stability analysis capability that develops a set of equilibrium curves that goes with each of these track parameters and conditions, and looks something like this. This is in the yellow dashed line. It gives you all the positions of equilibrium the track can have. And the good news is that this curve brackets the actual buckling temperature. In other words, the upper value here being P sub B max, the lower value being P sub B min, that kind of brackets or gives the upper low bound on where the track should buckle out. So yes, even though we don't know the exact buckling temperature, we'll know at least the upper low bound or the buckling regime when it occurs. And again, from basic stability considerations, if you're going to avoid track buckling, what has to be the temperature increase? Well, this bottom value over here, because below that, buckling does not occur. Above that, it's possible. So now the good thing is all tracks have a curve like this. You know, Each track has a pedigree curve that you see in the yellow there. So each track has a buckling regime and has this maximum and minimum point and a safe temperature increase value. That's the upper bifurcation point of the buckling curve. Bifurcation point. Okay, that's the one that's basically, if the track were to be sitting by itself with no loads, nothing on it, in static condition, that would be the temperature we buckle out. But because it's got dynamics, it's got uplift and other parameters, it buckles out somewhere below that. And if you want to avoid the buckling condition, we have to keep the temperature regime below this minimum point on this curve. Okay. Now, what defines the magnitude of these values? In fact, how large is the safe temperature increase value, and how big is the buckling regime? You can guess it's the track parameters and conditions. Okay. And there are many, many parameters, that come into the picture. Here I'm just listing the 4 or 5 major ones: track resistance, alignment defects and curvature, trend and dynamics, and this neutral temperature parameter. And I'm going to highlight 2 of these quickly for you. Starting with track resistance, also complex. It's got 3 components. Lateral, you typically think of it as a lateral spring. Longitudinal and rotational. The lateral is due to ballast. The longitudinal is due to fasteners in the ballast. And it's rotational was for the fastener rotational capability within the rail tie structure. Out of these 3, the most important one is in fact the first one, the lateral resistance. And that's basically the reaction offered by the ballast to the rail tie structure against lateral movement. How do we measure this thing? Well, in the US we use a technique called the single tie push test. Basically, you have a device that grabs the rail at the base, grabs the tie at the shoulder insert, which you can't see. You apply a lateral load through a hydraulic fixture to the rail into the reaction, and thus push the tie out of the ballast. And you measure its load deflection. Other measurement techniques in the past involved a discrete cut panel pull test, an entire continuous panel pull test, TLPT. Recently, Placer developed a technique called the continuous dynamic measurement as part of the dynamic track stabilizer. And we'll talk more about that in just a bit. And we even have an empirical model as part of our Rail Safe package. Question is, what happens when we push a tie in the ballast? What do we get? Well, we get a fairly complex set of signatures. So you see on your top left there. Depending whether the track ballast is weak, average, or strong. For weak, we get the blue curve. For average, we get the yellow curve. And for strong, we get the orange curve. Each of these have a elastic initial stiffness elastic limit. They have a peak value. They have a drooping resistance value, and eventually a limit resistance value. So analytically, it becomes kind of complex. And we generally characterize, ballast resistance in terms of these peak values you see over here. Just to give you a feel for what those are, weak tracks basically in the blue regime under 2,000 pounds per tie. Average, you see the yellow, and orange is strong. I'd like to point your attention to this green regime over here, called the marginal. That's defined as the consolidation range. That's the range that we have to basically quickly attain, because when we maintain track, especially from a ballast perspective, we're down in this regime. We're going to have to jump shift this green regime to get to the average condition, but we have some buckling safety. Now, as you can imagine, there are many parameters involved in terms of how high these peak values could be. They range from the kind of ties you have, concrete versus wood, the weight, shape, size, the ballast type, the spacing, so on and so forth. Issues with consolidation and maintenance, and even dynamic loads. We won't be able to go into all of these, this afternoon. I'm just going to briefly touch upon just a few. First being the impact of vehicle loads, namely this dynamic uplift. What happens to this track structure when you apply a load to it? Well, obviously, on the load, there's an increase in lateral resistance. In between the trucks, where there's a dynamic uplift, negative bending, we have reduced lateral resistance. How much reduction? Well, again, we have a lot of tests that tells us that in terms of the components of lateral resistance on a tie have three parts. One from the shoulders, one from the sides, and one from the bottom. And in terms of percentage contribution, the rough rule of thumb after many, many tests is that the shoulders give us about 25%, the sides gives us about 35%, the bottom around 40%. So what happens when you have dynamic uplift? Well, what happens is that you free up the tie bottom somewhat, and that means that we might lose as much as 40% of the resistance under dynamic conditions. And that is in fact why when tracks buckle out, they buckle out in between the two trucks, as you see over here, as shown by tests. Hence the importance of this dynamic uplift. Now, you might think that, well, you know, the shoulders contribute only 25%. Not a big number, right? Why do we care about it? Well, the answer is that because once we have dynamic uplift, and we lose up to 40% of the resistance, what keeps the track in place? The 25% on the ends and the 35% on the sides. Right? What else? Well, in curves, we have issue, again, with the fact that curves move back and forth. For example, you've seen pictures of this, I'm sure, in the past, where these curves on the thermal load tend to breathe in and out. And this lateral motion has a whole bunch of issues with it. Number one, when curves move in and out, the stress changes in the curves, therefore there's issue with neutral temperature. With the ballast reduced in the shoulders, I'm losing a lot of resistance. And of course, when curves move in, move out, it's not a uniform movement. In other words, the curve will not be perfectly nice and uniform. You think it's going to have some line defects. So when we couple all these elements together, reduced stress and neutral temperature, reduced lateral resistance, increased line defects, these are the three main ingredients for buckle track. So the bottom line here is we have to be very careful about maintaining ballast, shoulder width, even though it's only 25%, and especially in curves, it's a big impact on lateral stability. What about under the load in terms of increased resistance? Well, we know that vertical loads obviously add a lot to lateral resistance, and this brings into focus a parameter called the tie ballast friction coefficient. And that is a coefficient that relates the vertical load to lateral resistance. Namely, if I apply vertical load to the tie and attempt to push it out laterally, the resistance is going to be now the sum of the static condition and the dynamic condition, being the loaded condition. And that means that we have to add a parameter called this friction parameter times the vertical load to the tie. How to get this mu factor? You got to do tests. You got to basically apply different levels of vertical load to the tie and push it out in the ballast laterally and measure its loaded resistance. So from the difference of the loaded and unloaded, we can figure out what this friction parameter is. Bad news is that it's a complex parameter. It's nonlinear with load. It changes with tie type, whether it's wood or concrete. And this is one area that's very important for us because this parameter has a big impact on both the track buckling part of the problem as well as later on the track shift part of the problem. All right, that's it for about lateral resistance. I want to just briefly touch upon one more parameter, which is the maintenance and consolidation influence on lateral strength. We know that when we work ballast, we do surfacing, lining, tamping, undercutting, ballast is disturbed so that the track lateral resistance decreases substantially. How much? By as much as 40 to 60% in some cases. It requires us to get that back to regenerate the condition to better values. Okay? Now we have two ways of doing that. One is to what is called dynamic track stabilization, or DTS, or by traffic tonnage. Some of you are not familiar with the DTS, or dynamic track stabilizer. Basically a machine developed by Placer back in the early 80s. It's a machine that applies a vertical load to the track structure, coupled with a horizontal vibration of a certain frequency, 30 hertz, and you move this along the track at slow speeds, up to 1 mile per hour. What this does is, the combined effect is you reconsolidate the ballast particles and also increase this friction coefficient at the tie bottom, resulting in a immediate 30 to 60% recovery of lateral resistance. It's a really good thing to do. What about tonnage? Well, that's a bit more difficult for us because we know that many applications of vertical load will eventually give us some stabilization. But unfortunately to date, the mechanics and the rate is not well understood. How much tonnage do we need to get the track back to a safer value? Well, based upon some early European tests, the assumption was that you need at least 100,000 tons or 0.1 million gross tons of traffic to at least achieve the same as the dynamic track stabilizer. That's a lot of tonnage. It takes some railroads 2, 3, 4 days to get that on the slow speeds. It's a very, very bad thing to have in terms of putting on this traffic and consolidate, at a slow rate. Point being is that today's research has not really quantified whether the quality is really 0.1 or much more. In fact, more research is being done on it that says that we need much more than this minimum 0.1 million gross tons of traffic. And that's bad for the railroads because, again, it's slow the traffic, they lose revenue, and they need a better way to handle this whole stabilization idea. Yep. Yeah.
These numbers are a little surprising to me because what I remember is some of the graphs that are in Ernie Selig's book, where he shows it taking sometimes weeks to regain some of this stability, and I guess it's possible the tonnage on those lines was really light, but that wasn't my impression. Are you familiar with those experiments?
Well, it might take weeks and weeks if you're on Amtrak territory where you have one light,
but I mean,
light traffic.
0.1 MGT is not very much.
It's 100,000 tons. And the UP takes, for example, maybe 14 loaded trains to produce that, so they're okay. Some other areas that want less tonnage or shorter cars or constants, it takes a much longer time. And the problem that is this is slow the traffic, so this is impacting the foothill capacity, and of course revenue as well. And this becomes basically a new research, maybe perhaps a new R&D topic, because you don't understand this whole mechanics of ballast compaction under traffic loads. Okay. All right. So we talked about track resistance. Quickly, I will touch upon this other parameter for rail neutral temperature because that's very important. In my mind, it's one of the most important parameters as far as lateral stability is concerned. Basically because it sets up our zero reference condition from which we compute the temperature increase values. In other words, all our analysis will give us these nice buckling curves. You stipulate the minimum point of the safe temperature increase, okay, because tracks will buckle under that, they buckle above that. But all these values are reference to a neutral temperature condition. All those values are temperature increase values above neutral. Okay, so obviously neutral temperature is very important. What is it all about? Well, we know that stresses are made up by many components to give us the load P, a thermal, mechanical, and residual. If we integrate the stress over the area, making some assumptions, we get a simple equation that relates force to temperature. P equals E alpha times the temperature difference in the rail, TR minus Tn. TR is the rail temperature, and Tn is its magic neutral temperature. And of course, when these forces are high in compression, you get potential for track buckling. When they get high in tension, you get potentials of rail brakes and puller parts. So managing thermal forces really comes down to managing this parameter called neutral temperature, which you see in literature sometimes as T sub n, sometimes as RMT, sometimes as SFT. SFT for short for stress free temperature. And that's the definition. Neutral temperature is defined through this equation. It says that neutral temperature, Tn, is that temperature at which there's no force in the rail. There's a force in the rail is 0. And you set the P equals 0 in this equation, you get that the rail temperature equals neutral temperature, which is the definition. E and alpha are just engineering constants. E is the rail stress modulus of elasticity. A is the cross-section area. And alpha is the coefficient of thermal expansion. If you multiply those three together for a 136 pound rail, you get a number like 2600. That says that for a 1 degree change in temperature, I get a change in the force by 2600 pounds. Now, you can easily put some numbers in this equation. Let's take a nice high neutral temperature of 90 degrees, that's a good value. And a hot summer rail temperature, 130. Now these are rail temperatures, not ambient, okay? This equation gives us roughly about 100,000 pounds per rail. Big number, but not big enough need to cause any sort of buckling worries. However, if now this neutral temperature is no longer 90, but say it drops down to 50, then the equations give us, keeping the same rail temperatures before, now the force in the rail doubles, and this force level of over 200,000 pounds per rail is big enough to buckle the track out. So you might ask the question, well, that's nice, but does neutral temperature migrate so much up and down? And if so, why? Well, the answer is, unfortunately for us, yes, it does. It changes a lot because, first of all, the rail is not constrained in the rail tie structure completely. It can contract or expand longitudinally, move laterally in curves, and can even move vertically in track settlement. So rail kinematics impacts neutral temperature. Also, when the rail breaks, except for defect removals, what happens to the force? Force goes to 0 at the break. If the neutral temperature becomes the rail break temperature, so rail breaks also cause a large reduction in neutral temperature. Just to give you a feel for what's really happening out in track, this is a kind of nasty looking curve summarizing 5 years of testing on a major US railroad, a neutral temperature. The vertical axis is the neutral temperature. The lateral, the bottom is time, compressing 5 years of data in here. The green data is the high rail, the red data is the low rail. It's a 2-degree curve, concrete track, where the measurements are made by a device called the rail stress module. It's done by a company called Salient Systems. It's a rail attach unit. It's based upon a strain gauge concept. It measures neutral temperature, rail temperature, and rail stress in a continuous fashion. And that's what you see over here plotted with time. You might note the fact that typical installation regimes in the US are roughly between 100 and 110 degrees Fahrenheit. And you can see how much out of this range the RNT is. Kind of out of spec. Point your attention to these little values over here. Those are results of rail breaks. So the rail breaks was cut for defect removal, the neutral temperature changes substantially. These bands show daily variation. RNT varies even on a daily basis. Here roughly about 12 degrees, so on a 34-hour cycle, if I make this measurement in the morning, I get one result, measured in the afternoon, I get something 12 degrees different. This area over here is a result of track maintenance. When you move track back and forth, obviously you increase tension and compression in the rails, therefore you change the neutral temperature. So basically, the idea is that RNT is in fact highly variable, and its knowledge is very important for track buckling prevention and mitigation. I want to go back to this rear brake scenario quickly, just to give you a feel for what's really happening there. Unfortunately for us in the U.S. here, we have many rear brakes, about 80,000 per year. According to the FRA's accident statistics, we have about 100,000 internal rail defects requiring removal from service. Okay? And as you've seen before, when the rail breaks, its warranty goes down. And the problem is now when to make this repair, when to come back and adjust. If I don't make this adjustment before the advent of warmer temperatures, the track will become buckling prone. When I do come back and readjust, how to adjust a condition that I don't know what the warranty is. The railroads don't have these measurement schemes in place, so they have to guess at the depressed warranty condition to adjust. So basically the problem is that any given year we have over 180,000 locations on the railroad that might be potentially buckling prone. Big issue. Just to give you a feel for what's happening in a rail brake scenario so you get a better appreciation for this whole problem. Suppose we have a situation where the rail has a nice high neutral temperature of, say, 100 degrees Fahrenheit. And I'm going to monitor the neutral temperature here in terms of position 0 on the one side of the track, then the other side of the track. Suppose this rail breaks at 40 degrees Fahrenheit. What happens to the neutral temperature? You get something like you see in the orange curve. After you brake, neutral temperature goes down to 40 degrees, 40. There's a gap in the rail. It's about 3 inches for this condition. And you note that it takes this neutral temperature a long distance along the track to get back to the original high value. This length that it takes to get back to the high value is referred to as the rail brake influence zone. Okay. So what's the repair look like? Well, most railroads come middle of winter. They basically make what's called a plug repair. They fill up this gap, okay, by adding some rail to the structure, which freezes, locks in this reduced neutral temperature that you see there in the green, and that's the amount we have to readjust. The question is how to do it and when to do it. And the good news is that in the last couple of years, a lot of good research was done in this area. They have defined a set of tables based on, again, buckling considerations, when to come back and readjust so that so that we don't cause potential buckles early enough if you don't readjust. And number two, the issue is when you come back and readjust, then you have to cut the rail. You have to cut the rail out and unfasten a length of rail to get this warranty condition back to the target value. So the point is that rail brakes impact a lot of issues, okay, in terms of causing us this reduced warranty and these large influence zones. And now the railroads have a better idea of how to manage the repair of these conditions so that we retain back the initial desired high initial temperature. There's a lot of new work done in this area, so if you're interested in rail brake mechanics and some of the issues with lateral strength, as well as longitudinal strength, there's a recent paper presented at last year's ARIMA conference, but also it's a good report by the AAR. It's a TT report published last year that has all the good stuff in on how to adjust, what the issues are, what the parameters are, and what is the basic set of procedures and guidelines for adjusting rail. Just some factors of neutral temperature quickly. Both rails RT are as important for buckling potential control. The rule of thumb is basically that if the RT track is, if the RT track is in the good range, it's above 90. Most tracks out there have neutrals in the yellow regime between 70 and 90. If in this marginal range, that's not so good. And of course, if you're below 50, that's really bad. When the rail moves under normal operational scenarios, RT changes by as much as 20 to 40 degrees Fahrenheit. But as mentioned earlier, when the rail bakes, there's much larger change in neutral temperature. And again, through a lot of testing and and studies, we found that there are many locations in the railroad track that have naturally depressed or low neutral temperatures. Typically, as I mentioned before, the rail brakes. Whenever you have a location where the train's in very heavy train action, such as the bottom of grades, you have to push rail back and forth. And curves, pulled in winter time, and you approach rigid structures, switches, turnouts, crossings, and bridges, for example. These are also locations where RNT is suspect in most cases. And of course, if you have weak capacitors running, such as running rail condition, this also allows RNT to decrease. And you concretize, loss of tow load, and I'm sure you're familiar with the rail division problem. It's also an issue where RNT could be compromised. The last issue there is a big major impediment is that we still don't know how to measure neutral temperature accurately and non-destructively. And that's because over the years we tried many, many techniques, ranging from strain gauges to rail uplift concepts to ultrasonics, acoustics, magnetics, and so on and so forth. All these are good techniques from a physics perspective. When it comes to practical implementation, they all have issues with accuracy, issues with not giving us continuous data. Some of them are destructive, some are not, and they're not too cost effective. So this becomes one of the major needs in terms of R&D. I'll come back to this a bit later on. There are two systems in place today in the US that's being used mostly for test purposes. One I mentioned before earlier is the Salience RSM package. It's a rail-based package. It's got electronics in here, measuring rail stress neutral temperature and rail temperature. And they already have a situation in place where they accesses store data through a wayside reader. And that sends the data to a database management system, which is accessible from the internet. And they also have a situation where they can actually detect buckles by monitoring these conditions and issue a hazard warning. They can detect rail brakes. The big issue with this technology is that it needs a zero. It's initial calibration value. Okay. The other one is the rail uplift. And that's a concept based upon lifting the rail up with a known force, measuring its deflection, and you can apply that to a beam bending equation and back compute what the force in the rail is. This is the frame type structure that does it. And the problem with this thing is that basically it only works when the rails are in tension. So that's a problem because we don't know when the rails are in tension. Sometimes you're going to make this measurement at nighttime. Doesn't work in curved tracks. This curved rail uplift is very complex analytically. And of course, you have to unfasten a section of rail. In this case, 50 feet either side of the measurement point, hence becomes somewhat destructive as well. The good thing about the system is that it does not need any initial calibration. You need to measure know the rail cross-section area. So if you get one rail, you can make some profile measurements because that goes into analysis. So these are two current systems in place. Getting back to our stability issues in terms of safety criteria, it's very simple. We have to make sure that the loads in the track are less than the buckling loads. Now for a track, the longitudinal loads are the thermal loads. The difference between the rail temperature, T minus Tn, and less than the buckling loads. Buckling loads are, in fact, given by a stability criteria, the minimum point on this curve. Now, the good news is that on that part, we're okay. Over the years, we have done a whole bunch of model studies, did about 1,000 computations on different track conditions and parameters. So we have a pretty good understanding of what these buckling loads are. The bad news is that we don't know the other part of the problem too well, namely what the neutral temperatures are from which we compute these values. Again, as I said before, these are highly variable due to kinematics and rail brakes and defect cuts, and also very difficult to measure. This is, in fact, the most important problem in rail technology to determine and evaluate RNT continuously and accurately. So, how do we sort of get these safe temperatures to prevent buckling? We need three things: track parameters, we need a model, we need a safety criterion, and on the parameters, a whole bunch of them. They're ranging from rail type and size, curvature, line defects, lateral resistance. We touched upon some of these a bit earlier. That goes in the model. And the model give us this stability curve, stability diagram. And our safety criteria is basically this minimum point on the curve. As I said before, below this, buckling can occur or shouldn't occur. Above which it does occur. And that's our buckling safety criteria. The European standards are similar to ours, but they have two levels of safety. Level 1, just like ours. They believe that this minimum point on this curve gives them the safety desire, but also they have a less conservative value where they're actually allowed to go into the buckling regime by a small amount to give them a bit more added help in terms of managing their track condition. And how much they go up in there? About a quarter of the amount of the buckling regime. Okay. So, just a few things on the theory aspect. I know you might not be interested in this, but here it is. The model basically is a nonlinear classic beam theory, logic vectors. We've got the resistance values, the torsional, lateral, longitudinal as nonlinear parameters in there. This is the lateral plane. You have to couple this to a vertical problem, namely determine the dynamic uplift, and hence the reduction or increase of lateral resistance, which brings in the issues of track parameters and loads. You've got to worry about both tangent and curve analysis. And curve analysis is rather complex, as you can imagine here. And we've got to worry about boundary conditions, namely what sort of a buckling motion shapes do you expect to get. Many issues early evolved, this being the buckling shape, go shape 1. Turns out, to make things more complicated for us, the real buckling mode shapes are shape 3. Namely, it's got a main amplitude deflection up here, coupled by these lobes in the other direction on both ends. So it's mode shape 3, which makes it more complex mathematically because now we have two domains to look at. L1 and L, basically, and that makes it a bit more difficult in the analysis sense. And of course, all models have to be validated. And we've done a whole bunch of full-scale dynamic buckling tests. Here you see the last one done in 1987, where we actually derailed a train to prove the concept. So we're pretty comfortable about the model being good enough for determining the safe temperature increase values. Just to give you one quick sample of how these parameters come together in terms of safe temperatures. If you look at the 5-degree curve, for example, concretite track, it's US class 4 line defect condition, 136 bond rail, and different values of lateral strength. You get a diagram like this where the vertical axis is the track lateral resistance, and we have it color-coded to be weak, marginal, average, and strong. The bottom axis is the safe temperature as computed by the model. And this is our safe rail temperature. And these spoke lines are different neutral temperatures. So for example, if we have a weak track and a neutral temperature of like 60 degrees Fahrenheit, which is a pretty low neutral temperature, you can see that the safe temperature is only about 116 degrees Fahrenheit. Why is that unsafe? It's unsafe because normal hot summer temperatures where it can be much higher than that. Suppose we have a better track resistance. Let's say strong, again sitting on this low RNT curve. Now we're a little better. Now it's a bit safer because now we can tolerate real temperatures up to 140 degrees Fahrenheit. And those are pretty much the maximum summer temperatures we see out there. And here's the kicker. Suppose again we have weak track conditions. So we have high neutral. Now we have much higher safety in terms of track buckling. We can tolerate up to almost close to 160 degrees Fahrenheit, which again reinforces the importance of neutral temperature. If we can manage that R&D better, we can allow for a bit less in terms of ballast and so on and so forth. All right. If you're interested in a lot of details on this, in terms of a lot of parametrics, we only show you one case. Of course, we have to do this for tangents, 3 degrees, 7 degrees. You can look at different line defect conditions and so on and so forth. At least now we have a good methodology in place, understanding of what these numbers are. All those are available in this report you see down here. I think you have that available now, so feel free to look in there and get a better handle on how these parameters come together. Quickly, on the track shift side, this is the problem that I mentioned earlier, where we have the issue of multiple load passes with high LOV ratios. It's a moving load problem. Here the parameters are, again, moving axle loads, both static and dynamic lateral resistance, thermal loads, curvature influences, alignment defects, and a lot of work done in the past where it was attempted to look at the problem from a static point of view. And that's why the moving loads are very important. The idea was to put on a set of vertical lateral loads at one point in the track at X0, push the panel out and measure the load deflection response that you see over here, and find out which combination of LOVs give us a visual deflection. So it turns out this is not the way to go, because it highly underestimates the real problem, which is moving closer and closer and closer to this X0, each incurring possible lateral deflections. As I said before, here the issue is basically, or question was, what is the permissible mid-axis LOV to limit lateral deformations to safe, allowable values? Or conversely, you can ask the question another way, saying, given a particular LOV, what is my limiting ballast resistance so that I still retain good track geometry in the lateral direction? Getting back to the lateral resistance in this case, here we're going to worry about now the earlier initial part of the curve, namely the elastic limit and beyond that. And here the problem is, again, we have to look at the both loaded and unloaded resistance. Again, bringing in the friction coefficient parameter. And here the problem is that we have to be able to add up all these load cycles, loading, unloading, loading, unloading, as the load approaches a particular point of interest. So this hysteresis loop becomes very important in this whole mechanism. And that's the whole crux of adding up these incremental values of visual deflection to see what happens on the multiple load passes. The idea is, as I keep moving a load closer to the point, I have to calculate the deflection on the one load pass, and then at the end, sum up these residuals so you get a final value per load pass. Okay? And this is the whole crux of the entire analysis, where you compute this for many different combinations of lateral to vertical load ratios and find a value that you feel comfortable with in terms of a safety limit. You know that some values create large deflections. That's not a good thing. Some create zero or small deflections. So we have to figure out what is a good safety limit. The criteria is that lateral loads generated by, in this case, high-speed vehicles operating at a maximum cant, thermal load, and initial line defect conditions should not produce any permanent set larger than some value, x. The challenge for us, the question is, what is x? Well, again, there are two levels of safety. Level one that says that, hey, I'm going to have x be 0. There's find the L over V that produces 0 permanent set. It's the elastic limit criteria. Or level 2 says, well, no, that's too conservative for me. Let me allow some finite degrees of deflection, and this, such as maybe 0.1 inches, and this is a level 2 criteria. And the U.S. just enacted a safety limit, part of the passenger equipment safety standards just last year, where they adopted the level 2 concept, and it came up with the limit, as you see over here, that the lateral loads shall not exceed 0.4 times the vertical plus 5,000 pounds. Our friends in Europe, with their high-speed rail network, believe in this model, this level of safety. If you compare the two in terms of lateral loads allowed, our limit in the U.S. is the orange curve, and European limit is this yellow-green curve. You can see that their allowable is much less than ours, therefore they're much more conservative than we are. And I'll leave it up to you to decide whether you prefer our criteria or theirs. Of course, their issues are a bit different. They run much higher speeds than we do. But also their track conditions have to be better too, so there's a big trade-off in here. So, getting back to the issue of lateral resistance, and because that's the main component here, what's required to maintain the safety limits for high-speed passenger service? We have limits in the U.S. as well as in Europe. We have the criteria, that's very good. But how do they check against it? What lateral resistance is allowed to maintain those lateral loads? For us here, in terms of a high tonnage freight, we get a real serious problem nowadays, and that is that we're running very long trains, as much as 140 cars a train, with distributed power. It means you get power in the front, power in the middle, power at the ends, and these tend to add a lot of push-pull force into the rails and tracks and the vehicles in themselves, and they create a condition where we get forces acting outward on a curve, for example, in some cases, and inward in other cases, based upon the above draft or push force conditions in the applied by the distributed power. And here we don't have limits on lateral loads yet, nor we have limits in terms of ballast resistance. That's a hot topic nowadays because, again, a lot of areas trying to run these long trains, and curve movement becomes a big issue. So, again, what's the minimum ballast or lateral strength required for these conditions? Again, requires more R&D. So, the question comes up, all these issues, being said, have we reached the limit of lateral ballast strength capacity? Do we have enough ballast? Well, for these special cases where we're running long trains and such as high-speed trains, but especially with the freight tracks, the answer is yes, we have a concern with reaching the limit of ballast resistance because we know that we get buckle track, especially when the RNT is kind of low. You can have high resistance but still get buckle tracks. With high lateral loads, as I said to you just before, we have these dynamic loads of the track structure, and here, again, we may have reached the capacity of the ballast because we get a lot of motion in the track, especially in curves. How to improve? Well, first off, getting back to our usual need in this area, basically we have to measure liquid temperature. If you can't do that, we have to help the industry to implement what we call best practice guidelines to track and monitor those conditions better or work on those conditions better that contribute to a liquid temperature. We're talking about ballast a lot in terms of maintenance. Need to promote improved maintenance practices, especially in the regime of consolidation after ballast work. As mentioned before, the dynamic track stabilizer is a great technique to do this fairly quickly and efficiently. And what if we can't do all that? What's our last resort? Well, we have to consider alternative track designs aimed at high lateral strength tracks. Here's an example. See this unusual concrete tie that looks like a dog bone. It's got these high ends or wide ends, and these have a lateral resistance about two to three times the conventional concrete tie. These are being tested right now. They're produced by a company in Linz, Austria. It's called the HDS tie. They're being tested right now in Pebble Fast, but also in UP and high degree curve. And this might give us the extra strength required to maintain stability under these special conditions. Why is this good? Well, if we have such a huge high lateral strength, then we may not have to worry about neutral temperature that much, and we can maintain our curves much better as well. What else we need, obviously, to supplement all this? Much more R&D. And here's where I like to sort of get you people involved, because there's a lot of R&D needed in this area. I'm just listing 5 over here. Some of these we touched upon just a bit before. First one is develop a unified theory for lateral stability. We have a theory or model for track shift. We have one for track buckling. But many times the problems come together, they overlap each other. Okay? And we will need to get a theory that tells us under what set of L, V, and P loads, longitudinal, vertical, and lateral loads, the track is safe in terms of geometry. The model has to tell us that. Number 2, what is the mechanics of ballast compaction under traffic loads? We brought up the issue before of the needing at least 0.1 million gross tons, or 100,000 tons to consolidate. And again, our current research and test results indicate that that may not be enough. Is that enough? What is? So we need to look at ballast compaction mechanics under traffic loads. We need to look at the influence of axle loads, influence of train speeds, the many track types and conditions, wood ties, concrete ties, engine curved, efficacy of maintenance, and so on. Number 3, managing curve movement and stability under both thermal and dynamic loads. This goes back to our curve problem I mentioned earlier. Here's a figure that shows, how much change in neutral temperature you get when a curve moves in. The vertical axis is the change in neutral temperature. Bottom axis is degree of curvature, and the spoke lines are different amount of curve movement inward or outward. And as you can see over here, for example, if I have a 5-degree curve that moves in 5 inches, that's equal to reducing neutral temperature by about 30 degrees Fahrenheit. 30. It's a big change in curve movement. What do we need? We need some autonomous measurement system that monitors curve movement, that helps the ravers understand what the movement is in terms of R&D change, and use that in their maintenance practices. In terms of dynamic loads, like I mentioned, the LOV scenario. Again, long trains, DPU dynamics, lateral loads with the track structure, especially in curves. This requires an industry-mandated or driven R&D program to analyze this problem in terms of LOVs, ballast strength requirements, and key parameters. And finally, the Holy Grail. As I mentioned before, RNT. We need to have a method to effectively determine and measure neutral temperature. Challenges are, for the past 20, 25 years, you need to have a measurement technique that's accurate enough. Namely, measure neutral temperature between plus or minus 5 degrees Fahrenheit, which means that the measurement technique has to be impervious to things like microstructure, residual stresses, and various track types and conditions. The technique has to be also non-destructive, hopefully. You shouldn't have to cut rails, drill holes in a rail, or lift rails up. Okay. Deployable, durable. should measure the absolute force in the rail, not the relative, which means that we need a technique that doesn't require any sort of zero calibration. I mentioned before, the fairing systems module is great, it needs a zero calibration. The reluctant technique does not. Provide continuous real-time data. And continuous here means both in time and distance. Because neutral temperature is such a highly variable commodity, we need to make a measurement once a day, once every 2 days, sometimes even once every 5 minutes if need arises. So it's got to have continuous in time as well as distance along the track. And of course, it has to be cost effective for the railways to embrace the technology. With that, I'd like to thank you for your attention. It was a lot of fun for me. If you have any questions, now it's time to bring them up. Yes, sir. All right. All right. I cheated a little bit because I said it does influence, but indirectly it does. It does by the feature I showed you earlier, namely the rail brakes, right? The neutral temperature goes down substantially, right? If you don't readjust that in time and correctly before hot summer temperatures begin, what happens? The track becomes buckling prone. So effectively, rail brakes, by virtue of depressing neutral temperature and not readjusting properly, will create a summertime buckling prone condition. The exam question I usually give is, how can tensile forces produce buckling? And that's the answer. The nasty one. Yes, sir.
Force required to, the buckling force decreases. It requires less force to induce buckling. Did I interpret that correctly? It was one of the two graphs that you showed with the knee in it. One of them was the temperature impact of neutral temperature, and the other was the impact of deflection. And they looked about the same. It was maybe 10 slides back.
Well, let's backtrack. I think we do that, right?
Was that it? No, keep going. There.
Oh.
So on the right, the cumulative deflection. Actually, no, that's, sorry, I don't think that's it. Keep going back.
You want?
There. Go one more. No, keep going. Go forward again. Sorry.
Forward? There.
There. The bottom one.
Yeah.
So that suggests that as deflection increases, I'm trying to determine which way that goes, which is the cause and which is the effect.
But this says that if I have a lateral loader platform track structure, right? You know, it's got to go through a loading, unloading cycle into the track lateral strength. The peak strength might be over here, on the loaded, unloaded might be over here. But as I load the track up, you know, if I stay within this elastic limit and unload, I get no deflection, right? The trouble is that we don't stay many times in the elastic regime. Loads are such that I go beyond that. If I go beyond that and unload, unloading path is typically parallel to the loading path. That means I wind up with a finite residual deflection under each load pass. If I make many load passes, I have to add up these WRs, eventually coming up with a net deflection regime.
But at the point of that deflection, once that deflection has been induced,
Right.
Is there a change to the track structure that reduces the force required to deflect it further?
Actually,
I would almost think it went the other way because
very
you're taking tension out of the you're taking pressure out of the rail. You're essentially reducing the neutral temperature by allowing it to deflect, right?
Well, these are basically fairly small deflections, so the actual visual stress does not change that much in this problem. What does change is that once I start incurring deflections, visual deflections, this your line defect gets larger and larger. Okay? which brings the force level on it also larger and larger because the force increases with increased inflection. So in that sense, it becomes much more complex. So that's also in the model, by the way.
Okay, so you're sort of, it's not that the structure changes in a way that makes it require more force to deflect further, but you're concentrating the longitudinal stress at that one point.
Exactly.
So if there is a buckle, that's where it's going to
Exactly.
happen.
And also, it's multiple load passes. So one load does one thing, and next load does something else, and eventually you create a scenario where you get these things where on some LOV combinations, up to 3 passes, you might be, depends on what the LOV is, you want to be over here, which might be okay, but on the more LOV passes, you get larger and larger deflections.
But
That's not tolerable.
The issue with the cumulative deflection is just that you've created a point where the buckling is more likely to occur than anywhere else on that stretch of rail.
Correct.
Okay,
Correct.
thank you.
But this is, again, that's why I said before we have to eventually come up with this unified theory, because now this issue would bring the whole thing together. Because right now we analyze track shift as a lateral load problem versus buckling being just a compressive force problem. Okay.
That's the graph I was talking about, by the way.
Okay. Oh. Anybody else? Ernie? Well, conceptually it's fine, but we need to convince the railroads to really invest in that kind of a scenario because there's a whole new concept of not being the rail not being CWI anymore. It'd be more like a flexible structure. Some bridges have those elastic joints, Yeah. Well, the old chief engineer at UP, Bob Brown, was saying that, hey, I'm going to take out my welded rail and put back joints because it allows me to breathe. No, I know. Right. Yeah, and again, conceptually it's fine. Practically, you may have a lot of joint issues. That's why the railroads want to take out all joints. Anytime you have a joint, you have other problems. You got vertical impacts, you got joint failure. So it's that kind of stuff, But if you talk about an elastic regime, that's way of working it. That's right. Oh, okay.
This is a great presentation. Is this on?
That's okay.
Thanks so much. This is a tremendous presentation. One question is, going along with what Ernie was suggesting there, I don't remember if you showed any numbers in here, but Conrad talked about it a little in class the other day. Can you describe the zone of influence of elastic fastening systems in terms of their ability to control the longitudinal forces? Okay. Because the idea that Ernie had, you would have to have these joints very close to one another, right? I mean, it would almost have to go back to the... Okay.
Yeah.
1,000 feet, okay. I missed
Yeah,
it.
let me...
You don't have to go back to it if it's...
That's an excellent question because, again, I didn't spend too much time on rail brake mechanics. But, again, being a hot topic nowadays, and let's do it this way. Right. All right. With rail brakes, obviously, you have many parameters involved. The lower the rail brake temperature, the lower the resulting neutral, the longer this influence zone. That's number one. If I have handrails or elastic fasteners that have a better longitudinal capacity, that will reduce this influence zone. That will help. Okay? If I have every tie anchored, that helps. If I have every tie anchored, it increases. So the track's longitudinal strength plays a key role in how much of this influence zone you get. Was that your question? Yeah. And that's the way to manage. I mean, that's why, for example, if you have a high quality concretized track and it breaks, two things happen. The gap size are much smaller, therefore more manageable. And then, of course, this influence zone. When we pitched this to the railroads, they loved the idea, the concept, the theory, but they said, no way we're going to unfasten length of rail of this magnitude. We don't have the resources. In the past, we done only 200 feet. So we have to come up with a compromise on how to sort of give them a number that they're willing to do, at the same time be effective enough to pull this thing back to some reasonable value. But managing breaks is a tough issue because a lot of them out there, and especially for over 180,000 locations on the railroad, they have to fix. Yes, sir.
I also have a question. You in the presentation you talk about like between the wheels, due to the uplifting of the rail, the lateral resistance is reduced. But I have a little bit question about this idea because as we know that the wheel are actually moving, therefore the gap is the uplifting is only exists for very short time. At the same time, we're talking about the lateral instability due to two reasons. One is longitudinal load. The second one is lateral load due to the wheel. So I'm just wondering how would you understand this question in when the wheel is moving, and because we know that as you said that the uplifting of the rail is due to the distribution of vertical load. And at the same time, we know that the lateral load also only distributed in a short region. So yeah, so maybe I just want to know what's your picture when the wheel is moving.
Okay, two-part question. First of all, the wheel uplift by itself, okay, it's influenced by the vertical loads as well as the ballast foundation stiffness and the vehicle parameters, how far the loads are apart together. Okay? That's only due to the pure vertical load. Okay? Now you're asking about the lateral component. Now, good question. The buckling model doesn't have lateral loads in there. So that doesn't come into that part of the problem. It becomes on the track shift side of the house. The way you handle lateral load in the track buckling is the extra safety factor. Okay. Now that doesn't answer your question because you were asking me about the combination influence of vertical and lateral simultaneously, right? The issue is that once you have vertical load in the track structure, that's a good thing in terms of lateral resistance because it brings in the friction coefficient parameter. So I can take much larger lateral loads on the vertical loads, right? That's why this whole friction coefficient concept is very important to control that part of the mechanism. And again, in track shift, with progressive disalignment generation, this event becomes very important. Is that right? Anybody else?
I have a couple questions.
Yes.
I have a couple questions back to the point about sort of the stabilization of the track under traffic. You don't have to go back to the graphs. I just have a question. Do we understand whether that's a function of tonnage or wheel passes?
That's why we don't know. That's why I visit any research on, I call it ballast compaction mechanics under those scenarios, because we don't know whether it's a light load, heavy load. We don't know whether the speed effect is there. We don't know curvature influences in that consolidation process. It needs the whole new study. Now, Ernie Seelig back in old days did some of that, but under current track types of conditions, a lot of things are changing. So we have to kind of think the whole problem. Because the railroads, they're gonna, they don't want to, run all these trains for that purpose. It's damaging for them. They need something better.
Yeah, I mean, and one of the people who's not here today, but I think you know, is Professor Errol Tutumler, and some of his work on discrete element modeling of ballast occurs to me could be a modeling technique to address these questions, but obviously would need to validate it under test conditions as well.
Any research of that nature that would help us to better define how a train load scenario, multiple passes with tonnage, will help with the problem is very important.
triaxial, you see the load testing data for ballast materials. Granular materials in general,
Right.
you'll find that the permanent deformation accumulation is stress history dependent.
Right.
If you have heavy loads, you develop a certain amount. Okay, if you back off and the next train's got a bunch of lighter loads, they don't count as much.
Right.
So if you drop below those early conditioning levels, that's fine. And so building up stress history,
Right.
which is basically what you do when you condition at low speeds, et cetera, early on after tamping, that helps your cause. But if you reach a certain level and then you drop down to a lower stress state, your permanent deformation accumulation rate will decrease. So it's a
Exactly.
very complex issue.
And that's why that should be also part of the whole mechanics issue, And by the way, just to add another wrinkle to it, there's been some new data coming in that, and again, back to the effect of vertical load in the track structure. If I use the track dynamic stabilizer that does this vertical load and vibration and gives a nice increase in lateral resistance, the next train that runs on it does what? Pulls that down. It actually destroys some extent that initial level. Not by much, but enough to be measurable. Then after that starts creeping up slowly. Again, indicating there's some issue with compaction mechanics with one system versus the other system. It's a big issue right now. Anybody else?
We just ask if any of our internet participants have any questions. You have to type them into your, what is it? Chat box. They have to type it into the chat box, so. I don't see any typing going on, so.
Good.
Okay, looks like that's it for questions, and I want to thank Dr. Kish. If you think of any others and you want to talk about it further, we will be at the Blind Pig Brewery at 5:30. An opportunity to ask some more questions in a little more relaxed and comfortable environment. And we thank you, those online, and thank you for coming today, and just ask you to one more time express our thanks to Dr. Kish.